In this video, we will discuss interference of sound waves. Interference is an effect that happens when two or more waves overlap in the same region of space. We have already seen an example when two waves travel in opposite direction on a string or in organ pipes, and this produces standing waves. A string or a pipe is essentially a one-dimensional problem, and here we consider a more general case in 2 or 3 dimensions. So let's imagine that you have two speakers that get their signal from the same amplifier so that the two speakers emit in phase with each other. And let's consider 2 points in the room, right? The first point, point P, is at the same distance from the two speakers, and we call this distance D1. And the second point, point Q, is closer from one speaker than from the other. We consider the case where the difference in distance from the two speakers is half a wavelength. So the distance of point Q from one speaker is D2, and the distance from the other speaker is D2 plus lambda over 2. At both points, there will be overlap of waves from the two speakers, so we will have interference effects. Let's see what happens at point Q and at point P, and let's start with point P. As we did before, we will simply use the principle of superposition. So the signal at point P will just be the sum of the two waves, so we'll have A cosine kx minus omega t from both speakers, and kx will be 2 pi over lambda times d1 in both cases. Right. So I obtain 2A cosine 2 pi over lambda d1 minus omega t. So we simply get the same wave function but with a double amplitude, right? And we call this constructive interference. Now let's look at point Q. Again, we can use the principle of superposition. This time one speaker is at a distance d2, so we have A cosine 2 pi over lambda d2 minus omega t. And the second speaker is at a distance d2 plus lambda over 2. So here we can simplify because 2 pi over lambda times lambda over 2 is equal to pi, right? And now you recognize cosine something plus pi, right? And that is the same as minus cosine something. So we can write A cosine kx minus omega t minus A cosine kx minus omega t. And so the two signals cancel each other, and they're equal to 0. So there is no wave at all, and we call this destructive interference. Now, when two waves are in phase, but the starting separation is a distance equal to lambda over 2, which is what we just did in the previous example, then you see that the two waves produce destructive interference. Right? So when one wave is at a maximum amplitude, the other wave is at a minimum amplitude, and so they cancel each other. In the LibreText, you're given other ways to produce destructive interference. For example, instead of changing the distance, you can change the start time. Right? So if one speaker starts half a period later, then again, this speaker will emit a maximum when the other speaker emits a minimum, and vice versa. And so you get destructive interference also. And another example that is given in your LibreText is when there is a phase shift that is equal to pi. In that case, one of the speakers will have a signal that is shifted by pi compared to the other speaker. So even if they are at the same distance, and even if they start at the same time, because of the shift of pi, one speaker will be at a maximum when the other speaker will be at a minimum, and vice versa. And so their signal will cancel each other. I strongly recommend you read the LibreText on this section. It is very well written and it's not very long. Here, I'm going to give you an example. Destructive interference of sound waves is used in headphones with active noise reduction. And for those headphones, you have a small microphone that is going to record the ambient noise, and then there is a speaker that will re-emit the signal, but with the same frequency but shifted by half a cycle, right? That means shifted by pi. And so this produces destructive interference that will cancel the signal from outside for the listener.